Welcome back to the Deep Dive. This is where we really get into it, cutting through the noise on complex tech topics. We give you the insights you need.
Yep, synthesize knowledge for the real world.
Today, we're tackling something absolutely foundational.
Mm.
It really determines if you win or lose with generative AI. We're talking about the infrastructure, the whole system holding your knowledge.
And it's definitely not just about, raw computing power or having the biggest models. It's the entire data ecosystem we need to look at. Because the truth is, most organizations are just drowning in data they can't actually use well. So our mission today is pretty specific.
Right.
We're going to map out that whole journey from, let's say, chaotic, unused data, all the way to a governed, properly architected, and ideally autonomously managed infrastructure.
Okay, so we're pulling together 5 key ideas here. They're distinct, but really tightly connected. We'll hit the data chaos problem first.
And the governance you absolutely need.
Then the new architectures like lakehouses and vectors.
And wrapping up with this idea of self-driving storage, getting the infrastructure to run itself.
And the core idea, the main thesis that came through in everything we looked at.
It's pretty simple, really. High-quality, well-managed data. That's the non-negotiable starting point for any serious AI development.
Can't skip it.
Nope. If your inputs are messy, your outputs, well, they'll be garbage. Doesn't matter how fast your model is, the whole AI lifecycle, its efficiency, it all depends on getting those upstream processes right. Collection, cleaning, prep, all of it.
Absolutely.
Yeah.
And we're going to show you just how messy that upstream part often is. Like, we'll dig into this, frankly, startling stat that something like 68% of company data is dark data, just sitting there.
Yeah, unused.
We'll also unpack the differences, the really crucial differences between data governance and model governance. There's a great Lego analogy we found that makes it super clear.
Oh, yeah, that's a good one. Then we switch over to the tech solutions, how vector databases give you that real semantic search power inside a modern data lakehouse.
And finally, looking ahead, this self-driving storage idea. How AI is actually starting to automate the nuts and bolts of the data center.
Okay, sounds like a plan. Let's dive into this foundation.
So let's kick off with just the sheer scale of this challenge. Data volumes have just exploded, haven't they? Way past what old tools or even just people can really handle effectively.
Oh, totally. The numbers are kind of mind-boggling when you look at them. One study we saw mentioned 64% of companies are managing at least a petabyte of data now.
Wow, a petabyte, that's huge.
It's immense. But, the real headache isn't just the size. It's how spread out it all is. That data is fragmented, stuck in different systems, those infamous data silos.
The silos.
And that just makes it, basically impossible to get that unified view, that context that modern AI absolutely needs to work properly.
Yeah, because the AI doesn't just want data from one department's silo, does it? It needs the whole picture, the 360-degree view of the business to give you anything really useful.
Exactly. So let's clarify what we mean by AI data management here. It's more than just being a good beta steward, right?
Okay.
It's really about using AI technologies themselves to automate or, streamline those classic 4 phases of the data lifecycle: data capture, cleaning, analysis, and governance.
Right, the whole chain.
The big goal is still the same: make data accurate, easy to get to, and secure. But how we get there now involves intelligent automation, machine learning doing the heavy lifting, because only when data ticks those boxes can companies really use it for smart decisions and, get actual business value out of it. Hashtag PISM 1.2, the 4 core problems that impede business value.
Okay, but before we even get to the fancy AI automation, we need to face facts about the data we've already got piled up. Let's start with the transparency problem, this dark data thing.
Yeah, the sources we looked at make a useful distinction here between shadow data and dark data. They're related but slightly different. Shadow data is the stuff where maybe central IT or the governance team doesn't even know it exists. Like, think about someone in marketing spinning up a quick database in the cloud for a test, and then they just forget about it. IT has no record. It's literally operating in the shadows.
Okay, I see. And dark data.
Dark data is stuff that is on managed systems, but it's unstructured, totally unmanaged, and definitely not analyzed. Think old meeting recordings, customer service call transcripts, notes buried deep on shared drives.
Right, just sitting there.
Exactly. And the scale of this is just, wow. An estimated 68% of all enterprise data is dark. It's generating 0 value, but you're still paying for storage, maintenance, compliance. all of it.
68%.
Yeah.
That's an incredible amount of waste.
Yeah.
Just pure cost with no return. And I guess this often leads right into the second problem, the lack of quality, bad data.
It does. Bad data is basically information that's wrong, inconsistent, incomplete, or just plain old. And this is a massive business risk.
Yeah.
You could have the smartest, most advanced AI model on the planet, but if you feed it dodgy sales numbers or patient records that haven't been properly labeled.
Garbage in, garbage out.
Precisely. The output is fundamentally unreliable. And here's the kicker, the real insight that jumped out. Bad data can actually be worse than having no data at all.
How so?
Well, think about it. If you have zero data on whether a new product is selling, you're probably going to be cautious, right?
Mm-hmm. Proceed carefully.
But if you have bad data that tells you completely wrongly that the product is flying off the shelves, what do?
You get confident, maybe overconfident.
Exactly. False confidence. You pour millions into scaling up production, marketing, only to find out way later that the whole decision was based on corrupted data. The cost of fixing that mess is way, way higher than the cost of just not knowing in the first place.
Wow. That false confidence is dangerous. Okay, problem 3 ties back to what you said earlier, lack of accessibility. Those data silos again.
Yep. Beyond just frustrating the user who can't find what they need, silos create these inconsistent versions of the truth.
Right.
If your risk team calculates exposure using one set of data and the trading desk uses a slightly different, maybe incomplete feed, their view of the exact same situation could be totally different. They're literally operating in different realities.
Not good. And the fourth problem, security and compliance.
It's the constant challenge, isn't it? Data is always moving, coming in, getting changed, being shifted around. Trying to enforce policies and spot threats in that constant high-speed flow is tough, especially when you're dealing with sensitive stuff like personal info or patient data. Hashtag 1.3, the 4 pillars of AI-powered optimization.
Okay, so those are the big 4 problems. How does AI actually help fix them? You mentioned 4 pillars where machine learning is making a real difference.
Right, 4 specific areas where AI provides systematic solutions for managing that data lifecycle better.
Okay, pillar 1, data discovery. This is how we tackle that 68% dark data, right? Shine a light on it.
Exactly. We use things like intelligent classification and natural language processing, NLP. Machine learning algorithms can actually look inside files. Is this a contract, an invoice, a resume, a patient form?
So it's not just relying on file names or where it's stored?
Nope. It reads the content and automatically tags it with useful metadata based on what it means. That instantly makes all that previously hidden dark data searchable, even if it's scattered all over the place.
Let's dig into NLP a bit more. How does it bring structure to all that messy text, like emails or reports?
NLP uses something called entity extraction. It scans through unstructured text emails, reports, even meeting notes, and pulls out specific things, entities like names, dates, product codes, dollar amounts, and it maps those into structured formats. So suddenly, that huge archive of unsearchable internal memos becomes a structured catalog. You could actually ask it, show me all the reports mentioning Project X and its budget in the last 6 months.
That's powerful. Okay, pillar 2, data quality. We said if the input's bad, the AI model is basically useless.
Pretty much doomed, yeah. So automated data cleaning is key here. AI can handle things like checking if a zip code field looks like a zip code or correcting formatting issues automatically. It cuts down massively on manual work. But we also see AI used for synthetic data generation. This is where it gets a bit more nuanced.
All right, you mentioned a caveat here. Generating fake data sounds risky. When is it okay?
Well, let's say a record is missing a value, like an employee's salary. The AI can look at other complete records people in similar roles with similar experience and predict a likely salary.
Oh, okay, so it's an educated guess.
Exactly. For training big models, having a statistically plausible synthesized value is often better than just throwing out the whole record because one field is empty. But, and this is the crucial but, if the AI model doing the guessing is bad, if it just makes wild guesses,
then it creates more bad data.
Precisely. It poisons the well. So you need really strict checks to make sure the synthetic data actually preserves the statistical shape of the real data.
Got it. And anomaly detection fits in here too. It sounds proactive, like a guard at the gate.
It is. It's like the ultimate quality gatekeeper. The AI learns what your typical data set looks like over time. For example, your daily sales file usually has, say, between 95,000 and 105,000 rows.
Okay.
If tomorrow's file suddenly shows up with 1.5 million rows,
Wow.
or if the mix of product types drastically changes overnight, the AI flags it, it catches weird stuff, logical errors. That simple rule checks like, is this field null, would totally miss. It stops bad data before it pollutes everything downstream.
That makes a lot of sense. Okay, finally, pillar 4, security. You mentioned traditional security is rules-based. If this, then that. How does AI change the game, UEBO?
Yeah, user and entity behavior analytics. UEBA is cool because it doesn't just look for known bad things, like a specific virus signature. It looks for weirdness, deviations from normal.
How does it know what's normal?
It learns. The AI uses algorithms, often clustering, to build a baseline profile for every user, every server, every application, where they usually log in from, what time of day, how much data do they normally access.
So it gets a picture of 99% of regular activity.
Exactly. So if your database admin normally looks at maybe 15 sensitive customer records a day during office hours from the corporate network,
All right.
and suddenly that same account starts downloading 5,000 records at 3 a.m. from an IP address nobody recognizes, the AI flags that as a high-risk anomaly. A simple rule might miss it if the admin technically has permission to access those records.
So it's the context that matters.
Precisely. The machine learning spots subtle behavioral shifts that fixed rules miss. It dramatically shrinks the time window for an attacker or an insider threat. The tricky part, of course, is tuning it to avoid too many false alarms.
Right, you don't want to lock everyone out for working late.
Exactly. But that contextual understanding from ML is still a massive step up for security.
Okay, so AI can definitely help us clean up the existing data mess. But if you want to build AI you can actually trust, bet your business on,
Yeah.
you need rock-solid governance.
Absolutely. Which brings us to a really important distinction that trips up a lot of companies. The difference between data governance and model governance.
Two different things.
Two different but equally critical things. Governance is about structure, right? And you need structure at two key points in the whole AI process. This is where that Lego analogy really helps make it clear.
Okay, I liked this one. Let's start with data governance. This is the foundation, the prerequisite. This is the rules for the Lego box itself.
Right. Data governance is all about making sure your data sets, think of them as your individual Lego bricks, are all sorted, complete, they fit together properly, and they don't have flaws before you even start building anything.
Okay, so what makes a good Lego brick in this analogy?
Three main things: consistency, security, and high quality. Consistency means everyone agrees on what things are called and how they're formatted. Like we all use the same date format everywhere, or the customer ID field is always called exactly that. No variation.
Makes sense. Less confusion.
Security is about knowing which bricks are sensitive, personal info, financial data, health records, identifying them, marking them clearly, and making sure only the right people can touch them. This is fundamental for meeting regulations like GDPR or APA.
And high quality.
High quality means the bricks aren't broken or incomplete. Are there lots of missing values? Nulls? Are whole columns just empty? You also have to check for bias. Imagine using old hiring data to train a recruitment AI, but that data is, say, 98% male because of past biases.
That's a biased brick, a flawed brick.
Exactly. It's poor quality. If you try and build your Lego castle, your AI model, using biased or broken bricks, the whole structure is compromised from the start. You're baking the flaws right in.
Okay, so if data governance is about the quality of the bricks in the box, then model governance is about the thing you build with those bricks. It's the quality control for the Lego castle.
Perfect analogy. Model governance ensures the final structure, the AI model itself, is built correctly and stays stable over time. It looks at four main things for the model. Did you use high-quality, unbiased bricks? Good data. Does the model have a clear, well-defined purpose? Has it been rigorously tested? And is it being maintained properly to stop it from drifting or, worse, hallucinating?
And that testing piece is huge, especially with these big language models, right?
Yeah.
There are specific metrics we need to track for model governance.
Oh, yeah, absolutely critical. Things like ROUGE, for example.
ROUGE?
Yeah, it stands for Recall-Oriented Understudy for Gisting Evaluation. Bit of a mouthful, I know. But basically, it measures how good a machine-generated summary is compared to summaries written by humans. If your ROUGE score is low, it means the AI summary missed the key points or used completely different words. It might sound okay, but it's not capturing the essence.
So if I ask an LLM to summarize a complicated report and the REG score sucks, the summary might be grammatically perfect, but totally miss the strategic point.
Exactly. Fluent nonsense, basically. We also track things like knowledge retention. How well does the LLM remember facts you told it earlier in the conversation? Super important for things like AI customer service bots.
Makes sense.
And of course, latency. How fast does it give you an answer? That's still vital for anything real time. Model governance is about constantly tracking these kinds of metrics to prove the Lego castle is still standing strong and doing its job right. Hashtag 2.2, implementing the 4 guardrails for data repositories.
Okay, so we need this high level of governance for both the data and the models. How do we actually enforce it? The sources talked about a framework, like 4 guardrails for your data lake or repository. The key idea seemed to be shifting the effort way upstream, right to the beginning.
That's the core principle. Enforce quality right at the start so you don't spend 10 times the effort cleaning up a mess later down the line.
Right. So guardrail 1, standardized organization and documentation. This means getting the paperwork done before the data even hits the storage.
Yes, and this step alone can save so much pain later. Before any data gets ingested, you need documented answers. What is this data? PII, financial, etc. Who owns it? Who's responsible for its quality? What makes a row unique? A serial number, name plus date, how can it be joined or verified, and what are the timestamps and retention rules?
Why is nailing down the data owner so critical? Seems basic.
It seems basic, but think about it. When a problem pops up later, maybe a whole column suddenly becomes null values, who do you call? Without a clearly documented owner, data engineers can waste days just trying to figure out which system it came from and who's responsible for fixing the upstream pipeline. The owner gives you that single point of contact, that accountability.
Okay, that makes total sense. Then guardrail 2 builds on that, the automated ingestion layer. This is the enforcer.
Exactly. This is the non-negotiable rule. All writes to the data lake must be automated, no exceptions.
No more random spreadsheet uploads from users.
Definitely not. That's a Wild West scenario you want to avoid. Every single piece of data has to go through a standardized, tested, automated process that checks it against the documentation from Guardrail 1. It protects the integrity right from the start and makes managing the whole thing way simpler.
Okay. Guardrail 3 deals with what happens after the data is in. Storage and change tracking, especially during post-processing when data scientists start transforming things.
Yeah, because raw data rarely stays raw, right?
Yeah.
For AI, we often use object or document storage because it scales massively. The rule here is that any changes made after that initial ingestion, aggregations, calculations, new features being derived, all those subsequent writes have to meet the exact same rigorous standards as the initial write.
So you need a clear audit trail.
Absolutely seamless, traceable records of every transformation. If you build a model using aggregated sales data and later discover that aggregation logic was flawed, you need to be able to instantly trace it back through every step to the original raw data to pinpoint where it went wrong.
Makes sense. And the final one, Guardrail 4, data tagging for KI governance. You said this is vital for audits, especially with RG.
Critical for traceability, yeah.
Yeah.
You absolutely have to document which specific original data was used by which specific model to generate which specific output. And with ARGI retrieval augmented generation, the instruction is crystal clear. Data must be tagged properly before you vectorize it.
Why is the timing so important there? Before vectorization.
Because vectorization basically turns that chunk of text into a big list of numbers and embedding. Conceptually, it's a one-way process. Once it's just a vector, trying to figure out exactly which sentence and which original PDF document it came from is, well, it's incredibly difficult, maybe impossible. Tagging it first means you maintain that audit trail. Plus, it has a side benefit. You can reuse those computed vectors. Vectorization is computationally expensive, so if you've already tagged and vectorized a chunk of data, other models in the organization can potentially reuse that same vector, saving time and money.
Okay, so we've got clean, governed data. We've got the rules. Now we need the modern architecture, the playground that can actually handle the scale and the complexity that AI demands. And that architecture seems to be the data lakehouse.
Yeah, the lakehouse concept is really catching on. It tries to give you the best of both worlds. You get the simplicity, the massive scale, and the low cost of data lakes for storing all kinds of raw data. But you combine that with the performance, the data structure, and the reliability, like ASIC transactions that you'd normally find in a traditional data warehouse, hashtag 3.1 data lakehouses, and the RH strategy.
Strategically, why is pulling those two worlds together so important for AI?
Because the lakehouse becomes the single foundation for doing generative AI accurately. It brings together all your data-structured stuff like customer tables, unstructured video files, semi-structured logs from everywhere. Whether it's in the cloud, still on a mainframe, or in existing warehouses, it architecturally breaks down those silos we talked about earlier.
Right, one place for everything. But you said the real game changer is how it helps with the weakness of those big general-purpose AI models, the fact that their knowledge is kind of frozen in time or irrelevant.
Exactly. A huge foundational model might know, say, the general history of your industry, but it has no idea what your company's sales were last quarter or what's in your latest internal research report.
Okay.
The lakehouse architecture lets you plug a vector database right into that environment. And that's the key. It means you can feed the AI application current specific information from your own company represented as vector embeddings during the retrieval step.
And that's RAG, Retrieval Augmented Generation.
That's RAG. It ensures the AI isn't just making stuff up based on its old training data, but generating answers that are precise, up-to-date, and grounded in your actual real-time business knowledge. Hashtag 3.2. Closing the semantic gap with vector embeddings.
Okay, to really get RAG, we need to understand the tech that makes it possible, vector embeddings. You said traditional databases can't really search for meaning. They have the semantic gap.
Right. If you search a normal database for documents about, say, rising cost of manufacturing, it'll only find documents that literally contain those exact words.
Okay.
It won't find a report talking about increasing prices for raw materials or new pressures on the supply chain, even though conceptually they mean pretty much the same thing.
Because the old database only gets keywords, not the underlying concept.
Exactly. It doesn't understand context or semantics. A vector embedding bridges that gap. It's basically a long list of numbers, a numerical array or vector that captures the semantic essence, the meaning of a piece of data.
Like a mathematical fingerprint for meaning.
That's a good way to put it. And the core idea is geometric. Things with similar meanings end up mathematically close to each other in this high-dimensional vector space. The closer the vectors, the more similar the original data is in meaning.
Okay, slow down a bit.
Yeah.
How do you actually create these numerical fingerprints? How does a picture or a paragraph become a list of numbers that captures meaning?
It happens using specialized AI models called embedding models. There are different ones like CIP, often used for images, or GLOVE, or a sentence BERT for text. You feed your raw data, say a photo of a cat, into one of these models. It goes through many, many layers inside the model. The early layers might detect really simple things, edges, basic colors, textures.
Okay, so it sees lines and fuzzy patterns.
Right. Then deeper layers start combining those simple features into more complex concepts like, oh, this curved line plus these two pointy shapes looks like an ear.
Got it.
Finally, the deepest layers capture really abstract ideas and context. Okay, that ear shape plus this fur pattern plus the way the eyes look, that signifies catness. The output from these deep, meaning-focused layers is then compressed into that final vector embedding. It's like a dense numerical map of all the important semantic features.
So going back to that simple example, mountain sunset versus beach sunset.
Hmm.
Let's say our vectors have, I don't know, 1,000 dimensions. Maybe dimension 17 somehow represents water presence,
Yep.
and dimension 89 represents height elevation.
Yeah.
The vector database can then mathematically measure how similar or different those two images are based on the numbers in those dimensions.
Precisely. It calculates the distance between the vectors. They might be really close together on the dimensions related to color, like dimension 3 for sunset colors, but very far apart on dimension 89 elevation. This lets you query for something like, show me warm-colored images taken at low elevation, and it can find the beach sunset, even if the word beach was never manually tagged. It understands the concept. Hashtag tag 3.3 scaling vector search with ANN.
Okay, that's cool. But now we've got potentially millions, maybe billions of these complex vectors, each with hundreds or thousands of dimensions sitting in our lakehouse. Comparing a new query vector against every single one of those stored vectors.
Yeah.
That sounds computationally insane, like impossibly slow. Brute force won't work.
Yeah, brute force similarity search just doesn't scale at all. That's where approximate nearest neighbor search, or ANN, comes in. It's the key to making vector search practical at scale.
Approximate, so it's not always the perfect match.
Exactly. ANN algorithms make a trade-off. They sacrifice a tiny, tiny bit of absolute accuracy. They might not find the single mathematically closest vector every single time, but in return, they give you a massive speed up. Orders of magnitude faster. They find vectors that are extremely likely to be among the very closest matches, and they do it incredibly fast.
Okay, but if you're sacrificing even a tiny bit of precision, when does that become a problem? Like for really high-stakes stuff, medical AI, financial trading, can that small error matter?
That's the million-dollar question, and it goes right back to model governance. For those super critical applications, you absolutely have to tune the ANN system very carefully. Maybe you configure it for higher precision, even if it means the search is a bit slower. You have to validate that the level of approximation is acceptable for the risk involved.
Right.
But for many, many generative AI tasks, like finding relevant documents to feed into RAG, getting, say, the top 10 highly relevant results in milliseconds is far more useful than waiting seconds to guarantee you found the absolute single #1 best match. The speed makes interaction and scaling possible.
Okay, so how do these ANN algorithms work their magic? You mentioned a couple of acronyms, HNSW, IVF.
Yeah, those are two common ones. HNSW stands for Hierarchical Navigable Small World. Think of it like a multi-layered map, maybe like navigating Google Maps.
Okay.
At the top layer, you have very few points representing broad conceptual areas with links showing the quickest paths between them, like major highways between cities. As you zoom in, you go to deeper layers with more points and more detailed connections like local roads, then finally individual streets.
Ah, I see.
When a search query comes in as a vector, the algorithm starts at the top layer, quickly jumps across the highways to find the right general city or conceptual neighborhood. Then it rapidly drills down through the layers, following the increasingly detailed roads within that neighborhood to find the closest vectors very efficiently.
Clever. And IVF.
IVF is inverted file index. That one works more by dividing the entire vector space up beforehand, like creating different zip codes or districts. It pre-calculates clusters of vectors that are close to each other. When a query vector comes in, the algorithm first figures out which zip code or cluster it belongs to. Then, it only searches for matches within that specific cluster, or maybe a few neighboring ones. It basically ignores 90–95% of the entire data set right off the bat, which drastically cuts down the search time.
Got it. That brings it all together.
Yeah.
So let's just quickly recap that whole RAG process one more time now that we understand the architecture.
Sure. So the end-to-end RAG flow looks like this. 1. Prep. You take your internal knowledge base documents, wikis, whatever. You chop it into manageable chunks. Each chunk gets converted into a vector embedding, and critically, Guardrail 4 says it was tagged before this step. These vectors are stored in your vector database, probably inside the lakehouse.
Right.
2. Query. User asks a question. That question is immediately turned into its own query vector using the same embedding model.
Okay.
3. Retrieve. The ANN search algorithm, like HNSW or IVF, instantly compares the query vector to the vectors in the database and finds the chunks of text from your knowledge base whose vectors are semantically closest. This happens in milliseconds.
Finds the relevant snippets.
4. Generate. Those specific relevant text chunks are packaged up and sent to the large language model, LLM, along with the user's original question. They act as context or instructions for the LLM.
Is it the ground truth?
5. Result. The LLM then generates an answer that's not just based on its generic training, but is specifically informed by and grounded in those relevant chunks from your company's own up-to-date governed data. And because you tagged it first, you can even trace which original document provided the key information.
Okay, wow. So we've got the data right, the governance right, the lakehouse and architecture humming along. Now, let's shift focus down a layer to the actual foundation, the infrastructure underneath all this.
Yep. We need to look at how AI is starting to automate the data center itself, which is especially important because most companies live in a hybrid world, right? New cloud stuff mixed with older systems.
Like mainframes, they're still around running critical stuff.
Absolutely. Core banking, airline reservations, lots of crucial systems still run on mainframes. So effective integration means being able to bridge the gap between that legacy world and the modern cloud world, especially just understanding the terminology, hashtag 4.1, bridging the hybrid cloud divide, mainframe translation.
Yeah, the sources we looked at had this kind of helpful Rosetta Stone for translating mainframe speak to cloud speak. The key wasn't just the words, but showing the underlying concepts like resource isolation, workload management are actually pretty similar, just with different historical names.
Exactly. It helps demystify it. So on the hardware side, the mainframe's CEC or CPC, the central processor complex, that's basically the cloud's physical server.
Yeah.
The box.
Okay.
And an LPAR, a logical partition, which lets you run multiple isolated operating systems on one physical box. That's the direct ancestor, conceptually, of a cloud virtual machine, VM.
Right. Makes sense. And managing the work. The mainframe's WLM, the workload manager, sounds like it does a similar job to Kubernetes in the cloud, prioritizing important jobs.
A very similar function, yeah. WLM dynamically gives CPU cycles and resources to the most critical applications based on business policies. just like Kubernetes manages container resources and ensures high-priority services get what they need.
And defining those batch jobs, that old JCL, job control language.
Yeah, JCL is kind of like the forerunner to the shell scripts or YAML files we use today to define how a container should run, what parameters it needs, etc. Different syntax, same basic idea, telling the system how to execute a task.
But there's a fundamental difference in how they scale and handle resilience, isn't there? Mainframes seem built for tight integration, cloud more for distribution.
That's a really key architectural difference. Mainframes have this unique thing called a coupling facility, or CF. It's essentially a dedicated high-speed communication path that lets multiple LPIers, even across different physical boxes in what's called a parallel sysplex, directly share memory and access the same storage locks.
Okay, so they act like one big coordinated system.
Exactly. This super tight coupling means they can maintain data consistency across the whole complex without needing lots of data replication or sharding, which is common in the cloud. Cloud architectures generally favor loosely coupled, independent systems. They achieve scale and resilience by replicating data and services across multiple machines, zones, or even regions. It's a different philosophy, shared state integrity versus distributed redundancy.
Okay, so that helps bridge the hybrid gap. Now let's move fully into automation, this idea of self-driving storage, applying AI not just to the data content, but to the infrastructure managing the data.
Yeah, the analogy works surprisingly well. The goal is just like a self-driving car. Autonomous management of the storage resources. The system should be able to move data around, balance workloads, and proactively meet performance needs, all without a human administrator having to manually intervene for every little thing.
That's the fundamental requirement to even make that possible. You said the data needs to be mobile. Traditional storage is too locked down.
Yeah, that's the starting point. Old school block storage assigned to a specific server is very static. To get autonomy, you need mobility. The technical piece that enables this is often called a storage partition.
The storage partition, what's that?
Think of it as a logical container managed by the storage array itself. It groups together everything related to a specific workload. The actual data volumes, the hosts that need access, the quality of service settings like IOPS limits, and critically, the data protection policies, snapshots, replication, etc.
So it bundles the data and all its rules together.
Exactly. Because it's this self-contained logical unit, the partition itself can be moved fairly easily between different physical storage systems or pools within the infrastructure, bringing all its settings and data along with it. That's the mobility piece.
Okay. And the brain that decides when and where to move these partitions. That's AIOps AI for IT operations. What does it need to know to make smart decisions?
The AIOps engine needs a ton of data. The basics, of course. Capacity usage, IOPS, input-output operations per second, bandwidth throughput.
Standard performance stuff.
Right. But the really critical one, especially for user experience, is latency. How fast is the storage actually responding, usually measured in milliseconds? A system might have plenty of IOPS available, but if latency spikes, applications grind to a halt.
Okay.
Then the AIOps must understand the protection attributes tied to that storage partition. Does this data need snapshots every hour? Does it require synchronous replication for zero data loss? Does it need high availability HA within the data center or full disaster recovery DR to another site? These rules dictate where the partition can safely be moved. You can't move a DR-required partition to a system that doesn't support replication, for instance.
Makes sense. And you keep saying the AI needs history, not just a snapshot in time.
Absolutely fundamental. AIOps relies heavily on time series data. Looking at just today's usage tells you very little. The AI needs weeks, months, maybe even years of historical trends for capacity growth, IOPS peaks, latency patterns. Only then can it accurately predict future needs, spot potential bottlenecks before they happen, and figure out the optimal time to take action. It's all about prediction based on past behavior. Hashtags, hashtag 4.3, the evolution of autonomy. 3 phases.
Okay, so getting to fully autonomous self-driving storage probably doesn't happen overnight. It sounds like an evolution, building trust in the AI step by step. Phase 1 seems cautious. AI recommends, human decides, and acts.
That's the typical starting point. Build confidence. The AIOps engine does the analysis. It looks at the time series data and predicts, say, warning, storage pool alpha is likely to run out of capacity in 45 days, or workload beta is starting to experience latency spikes during peak hours.
Okay, it flags a future problem.
Right. Then, it uses its knowledge of the whole environment, all the available systems, their capabilities, their current load to generate concrete options. You could move storage partition X from pool alpha to system B or system C. And importantly, it provides a compatibility score for each option.
Compatibility score.
Yeah, it ranks the options based on how well the target system, B or C, meets the partition's specific needs for performance, IOPS, latency, and protection, replication, snapshots. It gives the human the data needed to make an informed choice. The admin reviews the options, picks one, and then manually executes the move. The AI predicts and advises, the human acts.
Okay, that builds trust. Phase 2 then takes it a step further. AI recommends, AI acts with human approval.
Yeah.
The human sets the goal, but the AI does the grunt work.
Exactly. Here, the administrator might say, okay, I need to deploy a new database. It needs 30,000 IOPS minimum and must have synchronous DR replication. They define the requirements. The AI ops engine analyzes the environment and suggests the optimal placement. System B or System C can meet those requirements. The administrator looks at the suggestion, maybe checks the compatibility score, and clicks Approve.
And then?
Then the AIOps engine itself performs all the complex, tedious configuration tasks autonomously. It creates the logical partition on the chosen system, assigns the volumes, sets the IOPS policies, configures the replication, sets up the storage network zoning, and presents the storage to the server OS. All automatically, often in seconds. The human is removed from hours of potential error-prone manual configuration.
That's a huge time saver. Okay, now the final step, the ultimate goal. Phase 3, full autonomy. Agentic AI making decisions and executing them without needing human intervention for every little thing. But isn't that risky? Where's the human oversight? What stops it going rogue?
That's the key question, right? And the crucial point is that even in Phase 3, the human role shifts from execution to policy definition. The agentic AI operates within strict guardrails, within policies set by humans.
Like what kind of policy?
For example, a non-negotiable policy might be, sensitive PII data must never be placed on a storage tier that lacks encryption, or critical production workloads must always have synchronous replication enabled. The AI agent is programmed to understand and adhere to these inviolable rules. If a potential autonomous action would violate a policy, the system is designed to stop, block the action, and alert a human administrator. So the human sets the strategy and the safety boundaries. The AI handles the operational tactics within those boundaries.
Okay, so the human is still in control of the rules of the road, even if the AI is driving the car. Let's use that high-value example. Handling big seasonal peaks, like Black Friday for a retailer, with this agentic AI.
Right. This is where Phase 3 really shines. The agentic AI has been watching the time series data for years. It knows that System A, the one hosting the main e-commerce database, gets absolutely hammered for 3 weeks starting in late November. It sees the historical pattern.
Okay, it anticipates the rush.
So weeks before Black Friday, maybe back in October, the KI autonomously decides, I need to prepare System A for peak load.
And how does it prepare it?
It looks at System A and identifies storage partitions belonging to less critical workloads, maybe internal development test environments, or the HR department's file shares. Workloads that don't need peak performance during the sale. The agentic KI then proactively, automatically, and non-disruptively moves those less critical partitions off System A and onto other suitable systems in the environment, like System B or C, that have spare capacity and performance.
And this happens while the applications are still running. No downtime.
That's the goal. Using the mobile storage partition concept, the migration can often happen transparently underneath the running applications. The KI handles all the complex data movement, reconfiguration, and validation automatically. The result is that when Black Friday hits, System A is cleared out, fully optimized, and has maximum resources available to handle the critical e-commerce surge. All done proactively and automatically by the AI, instead of humans scrambling reactively at the last minute. That's the power of infrastructure autonomy. Hashtag tag outro.
Wow, okay. That was quite a deep dive. We really covered the whole stack, didn't we? Started with the messy reality of corporate data, that huge 68% dark data problem.
Yep, face the chaos.
Then we laid down the law with governance. The Lego bricks and the castle, the 4 guardrails.
Building the foundation, right?
Then we got into the cool tech, the lakehouse architecture, how vector databases finally let us search for meaning, making a RAG possible.
The architecture for intelligence.
And we finished by looking at how AI is automating the very infrastructure underneath it all, with things like self-driving storage and bridging that hybrid cloud divide.
Yeah, making the foundation intelligent too.
So the big takeaway seems pretty clear.
I think so. AI data management in this broad sense isn't some optional add-on anymore. It's the fundamental investment you have to make if you want to get real value from generative AI. It's not about throwing out rules, it's about adding this smart, adaptive layer of control over the entire data lifecycle. That investment in data quality, in the right architecture, and in automation, that's what ultimately lets you build better AI faster and more accurately.
Okay, which leads perfectly into our final thought for you, the listener. We spent a lot of time emphasizing how crucial data quality is for accurate AI applications. And we just talked about how the self-driving data center relies on AI ops using tons of historical time series data, but the infrastructure itself to make decisions.
Data about the data center.
So here's the question. If good data is key, what kind of new governance frameworks do we need to apply to that AI ops time series data? How do we ensure that data is clean and accurate so the infrastructure AI doesn't start hallucinating its own needs and making bad autonomous decisions?
Ooh, that's a good one. Governance for the governance systems data.
It's governance all the way down, isn't it? Something to think about.
Definitely is. Making sure the data about the infrastructure is as trustworthy as the business data itself. That's the next challenge.
Thanks for diving deep with us today.
My pleasure.
We'll see you next time on The Deep Dive.